Hey, Eckhart.
Hey, Eckhart.
Okay, well, I think everyone has arrived in from the waiting room, so let's make a start. Good afternoon, good evening, and good night. Hello to everybody who's made it here. I know this is an awkward time for some folk, but welcome. My name is Beverly McKeon from Caltech. I'm one of the new co-lead editors of Physical Review Fluids, and it's my pleasure to welcome you to the first PR Fluids contribution to the Physical Review Journal Club effort. I'll ask everybody to mute themselves, please, and turn cameras off to preserve bandwidth for the presentation that will follow. Today's event will be moderated by one of the PR Fluids associate editors, Bruce Sutherland, who is here, and I will hand over to Bruce right now. Enjoy the event.
Great, thank you very much, Beverly. So it's my pleasure to introduce Eric Hester, who'll be presenting his recently published paper at this inaugural Physical Review Fluids Journal Club. Eric has nearly completed his PhD at the University of Sydney, working under the supervision of Geoff Vasil. And as he waits for the referee comments on his PhD thesis, he's now working as a research assistant with Martin Wesselberger at the University of Sydney. And starting in July, he's going to begin a position as the Hedrick Assistant Adjunct Professor at UCLA, working with Andrea Bertozzi. So I first met Eric in 2017 when he was a fellow of the Woods Hole Geophysical Fluid Dynamics Summer Program. And although Eric's PhD work was primarily theoretical and numerical, he made the gutsy decision at that time to work on laboratory experiments for his summer research project. And so over the 10 weeks of the program, working with two of his co-authors, Claudia Cenedese and Craig McConaughey, he began his research on melting ice by an underlying flow. And this work was later complemented by numerical simulations guided by his other co-authors, Louis-Alexandre Couston and Geoff Vasil. It's the culmination of this work that's resulted in the paper that he will present today. So I'm going to ask participants, if you have questions during the talk, please just put them in the chat. And then we'll field questions both by chat and raised hands in the discussion to follow. So with that, we look forward to your talk, Eric.
Thank you, Bruce. All right, so let's get this up. Oh, I can't quite share yet, Beverly. Okay. Thank you. And so, hopefully everyone can see this screen.
That's great.
Yep, without further ado, yes, I'm Eric, and I'll be talking today about how iceberg shape affects melting. So, first thing you know about icebergs, they come in a wide range of shapes and sizes, from the smallest bergy bits at around 10 meters in size through to iceberg B15, which was the largest iceberg ever recorded at 300 kilometers long. They're also geographically diverse, from Greenland fjords and Antarctic ice shelves, and even where I'm from in Sydney. So if you're ever on Bondi Beach, I recommend checking out Iceberg's Cafe. So to summarize the talk, we're interested in iceberg melting. I did some experiments, lab experiments of melting ice in warm salt water, and we saw some interesting effects. Weren't quite captured by previous models. So to understand what was going on, we built some numerical methods to simulate melting ice in warm salt water. And these simulations were able to reproduce our observations and explain what was actually causing them. So I'll also acknowledge this is a joint work. As Bruce mentioned, it started as a Woods Hole project with Claudia and Craig, who you can see here at the softball game. Also point out Bruce, who sustained an injury during his excellent softball playing. For the simulations, I use the Daedalus code. It's developed by my thesis advisor, Geoff, as well as his collaborators, Daniel, Jeff, Keaton, and Ben there. Another shout out to Keaton, who's in both of these photos, and is actually the one who wrote Daedalus in large part. And then to get Daedalus to simulate melting ice, we use phase field models. And this is work that was done with Louis Cousson and Benjamin Favier. And also you can check all the various papers related to this paper and others just here. So why do we care about icebergs? Yes, they are a shipping hazard. They're more than just a shipping hazard though. They are one of the largest sources of freshwater flux from the ice sheets to the oceans. And they do lots of other interesting things as they melt. They change shape, they can become unstable and tip over. And also in the news a couple months back, people noticed that the fourth largest iceberg ever recorded, A68, was headed for the South Georgia Islands. And this was going to be quite a problem because it was the size of the South Georgia Islands. Fortunately, at the last minute, it ended up turning away and breaking up, but had it collided, it could have really upset the ecosystem, scoured the seabed, damaged the fisheries and all that sort of thing. So we really do care about icebergs. And one of the most important aspects of icebergs is how quickly they melt. And the first people to investigate this question, Weeks and Campbell, wanted to know if you could use icebergs as a source of fresh water for deserts in Western Australia and South America. So yeah, they needed to know how quickly the ice was going to melt on the journey. And so they came up with this parameterization. And basically what it says is that the melt rate of the iceberg is going to be proportional to the temperature, and it's going to be basically proportional to the relative velocity of the water and weakly decreased with the size of the iceberg. And it's quite a useful parameterization, though it does miss a couple things. For example, it will not predict melting if there isn't any flow. So that was a bit unrealistic, and we wanted to compare these parameterizations with some actual experiments. So we had a recirculating saltwater flume. We've got dyed blocks of ice. We put them in the flume, and then we varied how quickly the ice was flowing past the, how quickly the water is flowing past the ice, as well as the dimensions of the block. And what we saw was quite interesting. So at high velocities, we saw a couple of things. Firstly, the melt rate was non-uniform. It was much faster melting off the front than off the bottom. And then within each phase, we also noted that the melting was itself non-uniform. So there was these really pronounced hot spots on the base, which melted much faster than the surrounding area. And then at lower velocities, we also noticed other effects, like despite the fact that the meltwater was fresher and should therefore be more buoyant, we noticed that some of the meltwater was actually sinking and driving some fluid flow. So to quantify our observations, we measured the final profiles of each of the ice block experiments. We saw that indeed, yes, the melting is non-uniform. And this was not predicted by the parameterization that I showed earlier, the Weeks and Campbell one, or any of the others that we looked at. It didn't predict the difference in melting between sides, and it didn't predict the variation in melting on each side. And indeed underestimated the average melt rate as a whole. And this issue got worse at lower velocities, where it predicted no melting at all. So, summarize where we are, we're interested in iceberg melting. We did some experiments. They didn't really agree with the previous models. And so to understand what was happening, we turned to simulations. So I'm going to talk about the code that we use to simulate melting ice, Daedalus, as well as the methods that allow Daedalus to simulate melting ice in salt water, phase field models. And then I'll talk about what they actually tell us at the end. So what is Daedalus? Well, Daedalus is a code for solving almost arbitrary partial differential equations using efficient spectral methods. So for anyone interested in this sort of thing, please check out the Vimeo page. There's a lot of cool videos there. There's also the project website and the methods paper. Now, a lot of people, when they hear spectral methods, they think, okay, it's accurate, but you can't do interesting geometries. And I'm here to tell you that that view is misplaced. You can do interesting geometries with spectral methods. Right, as a first example, this is turbulence on a sphere. Daedalus is among state-of-the-art full spherical codes. Now, what about more complex geometries? What about icebergs? And so that has been a large component of my PhD. And what I showed is that by reinterpreting objects and boundary conditions as source terms in your differential equations, it is possible to accurately simulate interesting physics in complex geometries using spectral methods. Now, how do we simulate melting ice in particular? So for that, we use phase field models. And the way they work is we start with all the standard equations, incompressible Navier-Stokes with heat and salt diffusion. And to that, we add a new variable, this phase field, which is just a smooth indicator function. It's 0 in the water and it is 1 in the ice. And it evolves according to a new partial differential equation, which is a reaction diffusion equation. And all it's saying is that if the temperature is above freezing, then you should melt. And then by simulating these equations with Daedalus and doing some mathematical analysis to calibrate it, it's possible to accurately simulate melting ice in salt water. And we can check out the Proceedings A paper for the details behind that. So, what did the simulations actually tell us? Well, our experiments found that the melting was non-uniform. And when we simulated these experiments, and what we found is that it's able to reproduce our observations, right? The melting is greatest on the front, it's lower on the bottom. And we also see that the melting on the bottom is again non-uniform. Now, the plot here on the bottom of the simulation is at the temperature. And you can see the melt rate of the block in red. And we see that what's happening here is as the fluid comes past, it's becoming unstable, it's generating turbulence and vortices, and these vortices are related to the increase in melt rate. Now, it's a 2D simulation, not 3D, so we do know that turbulence is going to be different. But the key takeaway is that we're getting agreement between the average quantitative melt rates as well as the patterns of the melting behavior. So that's a real success. And digging into it, we can, if we're looking at the non-uniform basal melting, we can see that it is the vortices driving this localized melting. So if we take a snapshot of the vorticity of the simulation, we can see the vortices in orange. And we can compare that to the melt rate at that time in red and see that what's happening is that as these vortices are generated, they're bringing up warm salt water towards the base of the ice, leading to a local increase in melt rate. And after that point, the vortices sort of spin up and then move on their merry way. Now, this is just one point in time. We actually want to see what's happening for the entire simulation. So what we can do is plot the melt rate of the ice along the base for all times. And what we see is that, yes, the melt rate it depends on space, it depends on time. On average, it's highest towards the middle, but we can correlate it with the vortices in particular by plotting the vortex locations throughout the simulation as well. And we can see, and this shows us that it really is vortices driving these occurrences of really high melt rates towards the middle of the block. And we predict that an analogous effect is going to be happening for real icebergs out there with non-uniform basal melting. What about lower velocities? So I mentioned that we saw some rather unintuitive sinking meltwater. And turns out the reason for this is double diffusion. So temperature diffuses faster than salt. And what is happening in this experiment is that the cold ice block is cooling down the salt water, making it dense before it is freshening it, making it buoyant. So some of it is sinking and driving these sinking plumes. And we can show that this is the case by running 2 simulations of this experiment. So on the left, we've got different diffusivities, as in reality, and on the right, we've artificially increased the salt diffusivity to make it equal to temperature diffusivity. And this shows that you need to have the different diffusivities in order to drive these sinking plumes. And the existence of these sinking plumes significantly affects the patterns of the flow field and the consequent melt rates of the ice. So the takeaway is that at low speeds, double diffusion really does start to matter with iceberg melting. So in conclusion, what are the main takeaways? The main thing is that iceberg melting is non-uniform. You can't really describe it with a single number. We ran experiments to investigate iceberg melting. We saw that it varied on each face, and it didn't really agree with previous parameterizations. So to understand what was going on, we built numerical methods to help simulate the phenomena. And they were able to reproduce both the quantitative melt rates of the ice as well as the qualitative melting patterns. And they were that, on average, melting on the sides of the iceberg is going to be larger than the melting at the bottom. Within each face, the melting is going to be non-uniform. In particular, at high speeds, vortex generation due to turbulence accelerates mixing of the flow and leads to localized increases in the melt rate. And at low speeds, double diffusive effects can become really important in affecting the flow and consequent melt rates of the ice block. So there you go. I hope I managed to convince you that iceberg melting is an interesting problem. Thank you.
Thank you very much, Eric. That was a lovely talk. So for anyone who would like to ask a question, again, you can put it in the chat or you can raise your hand. And if you're not familiar with Zoom, to raise your hand, you go to reactions, which is near the bottom of the screen. Click on that and you'll see a raise hand option. So please, if anyone has any questions or comments, please do so. Daniel's got his hand up, so we'll begin with him.
Hi there, Eric. Thanks for the great talk. I had a question about the double diffusion. So yes. you mentioned this picture of the iceberg cooling the salty water, which causes it to fall. But if the water's less than 4 degrees Celsius, then cooling it will make it more buoyant. So can you describe how this works with this nonlinear equation of state of water?
Yeah. So the nonlinear equation of state is an important aspect, but for salt water, the density minimum at 4 degrees Celsius actually goes away. Right? The temperature minimum requires fresh water. We're talking about salt water, and so because of that, that's a freshwater effect is my basic response. And
great, thanks.
I hope that answers the question, Dan. If it didn't, I can get into more detail.
Let's have a question from Eckhart.
Okay, yes, thanks. Very nice talk again. I was going to ask about the same thing, the nonlinear equation, relationship between density and temperature, but you answered that already. How did you define a vortex, or how did you identify a vortex where you correlated the vortices with the melting rate? What kind of a definition for vortex did you use?
Yes, that's a very good question. And there's not really an established definition for vortex. But so what I did was I looked at a couple definitions. So for one thing, you can look at the vorticity. Another thing you could do is the cube of ice criterion, or the Q criterion. I did both. And then I look at what is the depth averaged vorticity, or the depth averaged Q criterion at each point in time. And then you threshold that depth average of the vortexness. And you can see that, or you can pretty clearly see the vortices pop out. And it doesn't really matter what precise definition you use. You can use the Q criterion, you can use the vorticity. You end up getting pretty clear indications of the vortices coming out either way. So here it's specifically depth average vorticity.
Okay, I was just wondering to what extent the boundary layer vorticity right at the interface might interfere with this definition of vortices and you know, with this correlation.
Yeah, again, I mean, that very good observation, and it turns out to not actually matter that much because, you know, the vortex is sort of clumped up the vorticity generated by that boundary layer. And so if you take a depth average and you threshold appropriately, it's going to capture the vortex and not the shear layer.
Okay, all right, thanks.
Just to follow up on that, Eric, I was wondering, you probably did the simulations at the same viscosity as the experiments. And I was wondering if you were able to generalize this and come up with an idea of the length scale, how far from the nose of the glacier would this vortex effectively saturate to give you that first dip?
Yes.
Is it universal or is it viscosity dependent?
So it's a little hard to determine the viscosity dependence entirely through the simulations because this simulation of the experiment is already really pushing the limits of what we could do with the DNS. Now, from the experiments, what we saw is that basically that length scale of the localized increase in melting was going to be a small multiple of the depth of the iceberg. That was basically what we found. And that's that's like a viscosity independent measure. Now, you know, at low viscosities, it will behave differently, but we expect that, you know, once you're at Reynolds number 1,000,000, you know, you may as well be Reynolds number infinite. And we think that it's basically going to depend on the, you know, a small multiple, maybe 2 or 3 times the depth of the iceberg.
That's great, thank you. Let's take a question from Beverly.
Hi, Eric, I enjoyed your talk. In this short format, you didn't have much time to address the shape of the iceberg, but I mean, if I look at that image that you've left there, there's a sort of a provocative question about small versus large and the leading edge shape relative to the vorticity, the vortices that are generated. Is there anything you can say about what happens as the icebergs get very small? Is there a limit there where that vortex led mechanism is not important?
Yeah, okay, very good question, Billy. So what happens as it gets smaller and as it melts? Well, you know, there's a lot of different effects taking place. You know, at one level, we have different average melt rates off each face. And so it'll come to be dominated by one or the other side of the object. But if we're talking about more specifically, like what's happening here, we can see that, say, this front edge here is becoming more and more sloped over time from the melting. The melting on the front face is also non-uniform. And the fact that it's sloping is likely going to change the behavior of the turbulence behind the leading step. And that may be leading to longer length scales for that generation of vortices and increase in melt rate. So, you know, it smooths out over time. That could alter the location of the hotspot.
Thank you.
Let's take a question from George, if I'm pronouncing your name correctly.
Yes, hello. Just a question about the boundary condition. Are they adiabatic or?
Sorry, so the boundary conditions for the
temperature.
Sorry,
for the temperature. The boundary condition for the temperature.
Okay, so the boundary conditions for the simulation are the same as the boundary conditions for the experiment, which is we had a tank and we specified the velocity at the incoming side, and we also specified the temperature. So we have Dirichlet boundary conditions on the left. that may not be apparent from what I'm showing you in the movie, it's the simulation, because I've zoomed in onto the block, but it's embedded in a much larger tank, just like in the experiment, where we specify incoming temperature, salinity, velocity, and it is flushed out as it goes through the rear of the simulation.
So it's not the same one of the temperature at the left. It's not the same of the water.
The temperature at the left,
of water.
both experiment and simulation, is specified to be 20 degrees Celsius. And then at the end, it goes through a filter, which restores it. And then it comes back in on the left as, again, 20 degrees Celsius and 30 degrees, 30 PSU.
Okay, thanks.
As you were saying at the end of your talk, Eric, this is a bit of a playground in terms of where you can go from here. This is largely a two-dimensional problem at this point. And so I was wondering, first of all, did you ever see streaks underneath the ice, or is it more or less uniform across the span? And do you have plans to look at, say, localized icebergs with flow going laterally around the berg as well as forced underneath?
Yeah, so we did see some, 3D effects in that if we are looking at the sides of the block, the sides also had these localized melting hotspots in the same location. But the behavior along the bottom was really quite two-dimensional. As for where to go next, yes, 3D effects really do matter, right? And if you're talking about a large block, the presence of that third dimension is going to change things. It might depend on the geometry of the iceberg, but yeah, that's absolutely something that I'm interested in, right? How does 3D affect things rather than just 2D?
So we're going to end on a mathy question. We have a question in chat from Satwik Mitra asking you to explain the differential equation, but maybe Satwik, you can turn on your microphone and be a bit more specific about what you're asking.
Yes, sir, this equation.
Is this the differential equation you're asking about?
Yes, sir. Yes, sir. Yes, sir.
Oh, okay, sure. So I, in the interest of brevity and clarity, I omitted the full system of equations, right? And that full system is available in the paper. But basically, like I said, you have the standard system. It's incompressible fluid dynamics with heat and salt diffusion. Then, to that system, you're adding a new equation, the equation that you can see here. This is a reaction diffusion equation. And the first term on the right-hand side is the term that makes the phase field stick to 0 or 1. So it's trying to keep things as ice or water. And it's unstable in a sort of equal in between those points. The next term is saying that the temperature, or more accurately, the thermal forcing, so it's the temperature and also the salinity, are an additional force in this equation, which just say that warm things cause the phase to decrease. And then you also have to go back to the other equations and add other source terms. So as you melt, you release latent heat. So there is a cooling effect in the temperature equation associated with melting ice. But again, if anyone is interested in how this works, you can check out the PRF paper or the methods paper in proceedings. I hope that answered the question, Satwik.
Okay, sir. Thank you.
Well, that's lovely. Thanks you again, Eric, for an excellent presentation. And I want to thank all the participants for showing up and asking some nice stimulating questions. And a great plug right at the end there by Eric. Do proceed to go and look up the paper yourself by Eric and his co-authors if you've not done so already, and feel free to browse the rest of the journal while you're at it. So with that, we'll close today's Journal Club. We look forward to doing this again. And I wish you the best for the rest of your day or evening or whatever you have ahead of you. Take care, everyone.
Thank you.
Bye-bye.